the reason is that singularities started to be taken into account, mathematically speaking, at that time, with 3 seminal papers, okay? And because until that time, basically singularities were weird points where functions exploded or did weird things, so nobody really focused on that. But at this time, there were 3 papers. The first one was by Airy. I don't know, probably many of you know the Airy function. So that's basically what this paper was about. And what he did was a work on supernumerary rainbows. Okay, so here you have a supernumerary rainbow. I don't know if you're familiar with it. It's when you have several copies of the original rainbow, and they have different intensity. And all this happened because 2 centuries earlier, Descartes already discovered how rainbows were formed. So this is the main mechanism. You get the light from the sun. It gets refracted and reflected in the spherical droplets, and then you get the rainbow, which is seen by the observer. And Descartes already discovered that the angle at which you would see the rainbow is 42 degrees, and so on. So this mechanism was well discovered by Descartes, and the important thing was that Descartes didn't have a formulation that accounted for these supernumerary rainbows. Okay, so he could only tell what was going to happen with one rainbow. He couldn't explain why. So after that, a few years earlier, I think it was Thomas Young, basically said that the way to reproduce the supernumerary rainbows was by using wave physics instead of ray physics. So this is basically rays of light that get refracted, reflected, and so on. But if you want to get this, you need to talk about waves, not about rays. Okay? But he couldn't give a mathematical formulation for that. And that's when Airy came in. And basically what he did was to first show that the rainbow is a type of caustic. Caustics are basically this phenomena that you see in a river when you look to the deep end of the river, and basically the light comes in, crosses a curved medium, and that allows the light rays to focus at different regions. So these are the caustics, the places where it's very, very intense. Okay, so basically the rainbow is a kind of caustic. You can see it here because they come parallel, and then they focus on some regions and defocus on some other regions. So that's why it's a caustic. And basically, in that language, these are singularities where the intensity goes to infinity. Okay, so I'm going to talk about the singularity in intensity in this case. So Airy basically what he saw is that you can regularize these infinities by doing the wave analysis, and that's done with his famous integral. And with that, he was able to reproduce the shape of the supernumerary rainbows. Okay, and you can see how these oscillations basically are related with these several rainbows that you see there. So this was the first paper, trying to study in detail singularities. Then there was another one, which was very surprising to me when I read about it, by Wewell. And he basically studied tide dynamics. Okay? So he was interested in the dynamics of tides in different parts of the world and how they correlated. So he started doing this kind of diagrams. This is, I think, an original from his paper. And basically, you can see here a number of lines that go from 0 to 11. So these are hours of the day. Okay, so 12 hours is the period of the tides that you have. And basically, these are the maximums of the tides in the sea between England and Holland. Okay. So basically what he saw is that if you start correlating these measurements, you see a counterclockwise rotation with a node in the middle. Okay? So he's the one that started to use these cotidal lines and discovered the rotatory tidal waves, which are this rotation that you see around this point, which is called amphidromy point. Okay? These are places where the tide doesn't move at all. It's fixed at height. So in contrast to the previous case, these are phase singularities, not intensity singularities, and they have zero intensity because it doesn't move, basically. Okay, so examples of this, you can get them in physics in many different fields. So in optics, you can get an optical vortex, which is the same thing, it's a phase singularity. In superfluids, you can have a quantum vortex, or in superconductors, you can have a quantized flux. Okay, so these are all phase singularities in that sense. Here, I think it's interesting. You can see a whole map of the amphidromy points in all the oceans in the planet. And there aren't too many, and it's very interesting. This tells you all the information about how the tides move and so on. So this was the other type of singularity that he discovered was interesting and had physical effects. And the last paper of these miraculous theories was by Hamilton, the one of the Hamiltonian that we'll use in physics. Okay. And this is about singularities of polarization. Okay. So basically, he was studied what are called birefringent materials. These are materials where the refraction indices change. Okay. And basically, well, the general phenomena is seen here. You shine light into a material, and then, for example, in this case, these materials have a different index for different polarizations. So the light ray separates in two components, and if you observe from the other side, you see two rays coming out, okay, with different perpendicular polarization, for example. So he focused on these kind of materials, and in particular, he was interested in what are called biaxials. Okay. So in biaxials, what happens is a very funny phenomena, because are the most complex one. All the indices are different, and in uniaxials, which are slightly simpler, only have one optical axis, you, for example, could have this phenomena that I just told you. You shine light, and it separates into rays, and you observe two at the other side. But you can insert this light along the optical axis, and they wouldn't separate. They would just go together at this particular direction of incidence of the light. Okay. But in biaxial crystals, what happens is that even if you look for this condition, they have two optical axes. What happens is that you get a hollowed cone of light. Okay, it spreads the light; it doesn't go in a straight line, and it's a hollow cone. And this was observed. And for what I read, basically, this is the first time that there was first a theoretical proposal of this phenomena, and then it was measured. So it was a big thing at that time. Okay, so this is basically the three papers that, according to Berry, started this field. And interestingly, during this time as well, Foucault developed his theory of his force and so on. And this is going to be related with all this, because Foucault, basically at the end, can be explained in terms of a geometrical phase. And it's basically the same phenomena as I described for the other cases. And I'm going to show you all how it ties up. But this is going to be very important now to explain the planetary waves, so let me introduce it very briefly. So the Foucault pendulum is basically described by this force, okay, which is a force that you measure when you are an observer with some velocity, and you are in a rotating frame. So you see that there is a force that deviates from a straight line. Okay. So in general, this force is very small at our scale of the planet Earth. But there are two regimes where it can be important. So one is the long time scales, which is when the Foucault pendulum appears. Basically, you wait for a long time, and you can see the deviation in the plane of the oscillations. And the other one is when you have slow velocities and long distances. Okay, so here omega is the rotation of the Earth, basically the angular momentum of the Earth, and T is the time. Length is, in this case, for example, length scales in planetary scale, and U is the velocity of, in this case, for example, ocean or wind currents in the atmosphere. Okay. Importantly, for Foucault's idea, the Earth curvature for the Foucault pendulum, the curvature of the Earth is very critical, because it's basically what gives you a latitude dependence on the angle. But you can basically work with Newton's law, introduce this force, the tension, and so on, and rewrite everything as an harmonic oscillator with a friction. Okay, and with that you just get an analytical solution for the oscillation in the plane, the deviation due to the Coriolis force. Okay. That's what you get when you write these coordinates and so on. I mean, basically you start with Newton's law. Oh, it means that basically it's not a dissipation, it's just a change of frequency in the plane, basically. Yeah, it's not a damping. So it's like another time scale, which is going to be slower and modulating the main oscillation. Okay. So this is the original way to get the deviation in the plane of the Foucault pendulum, but there is another way, which is very simple, and I think it's intuitive for people working in geometry and topology, and it's the following. So you don't need to know about Coriolis force or anything like that. We're just going to use something that is called parallel transport of vectors, okay? And what is called adiabatic evolution. So imagine that you have a sphere. Okay, this is going to be our Earth. And you want to study the trajectory of a pendulum. That is, we are going to assume confined basically in a plane. So the height where it oscillates is very, very low. So you can just work in X and Y coordinates, let's say. And then you let the pendulum oscillate and wait for one oscillation of this pendulum. So when that happens, the Earth has rotated a little bit. So if you were initially, let's say, in this tangent plane here, now you are in another tangent plane here, which is different to the original one. So at this time, by Levi-Civita, was asked the question, how can I compare the original vector and the other vector when I have changed the tangent plane? So this is basically the problem of parallel transport of vector. And the answer is basically that to make the minimal change in the vector, what you have to do is to take a vector that has that the difference with the original one is just perpendicular to the plane. So if the difference between the two vectors is just normal to the tangent plane, that's the minimal change that you can do. Okay. So if you do that and you calculate what is the angle of rotation, you basically get Foucault's result just from a geometrical analysis where you impose that there is a curvature because of the sphere and there is an adiabatic evolution during the oscillation of the pendulum. You don't need to say anything else and you get the angle. And the reason why you get this angle in such a simple way is because it's a geometrical result. It doesn't depend on the dynamics or on many other things. It only depends on the trajectory that the pendulum has followed during the rotation of the Earth. Okay? And there are very funny ways to get the result, for example, by putting a cone with the same trajectory at the latitude that you want, and then you unfold it, and you compare the vector, the initial and the final vector, and this gives you the same angle. So there are very funny and fun geometrical ways to get this. But all I want you to understand is that you don't need to do the whole dynamics of a system to start learning about these processes. You can just do a geometrical analysis, and you will get the same result. Okay. So, for example, this result has been observed in shear waves on earthquakes. So shear waves are the ones that go with an S profile, okay, oscillate up and down, and follow the same deviation because it's a geometrical deviation, it's very general. And this is very similar as well to the quantum phase that I will go to it later on, in the sense that it's basically an angle that depends on the integral of some curvature over some path that you have followed. Okay. So how do we connect this with topology? So the way to do it is that here, for example, the angle depends on the trajectory that you followed here. So this sigma here in the integral is basically this contour that you are following in the sphere. So to go to topology, you can basically say, what happens if my volume, where I'm integrating the surface of the Earth, is a closed manifold, so it's completely closed, it's not open like a flat space, and I integrate a trajectory that covers the whole sphere. So it doesn't make sense geometrically because you're integrating everything, but when you do it, you get a number which is called the Euler number, and for the case of the sphere and the Foucault pendulum, it's just 2, 1 minus g, where g is the number of holes in your compact space. So a sphere doesn't have any holes in it. So this is the genus is 0, and you get 2. Okay? And this is basically telling you that a sphere has 2 singular points. And that's why you cannot map a sphere to a plane. So basically, the typical way to explain it is with the Hairy-Ball theorem for a sphere, that if you have a ball, a head, and you want to comb the hair, you cannot comb it all in the same direction without getting a singularity. You will get either the singularity here and the other one here. One goes away, and where they meet, all the vectors. And that's the 2 numbers. And it's basically telling you about the topological invariant of this system. Okay? Okay, so that's how I wanted to connect the introduction of topology and geometry to these different fields. And now let me move to planetary waves. Okay. So the way, so this is a friend and a collaborator of mine, and it's one of the authors of this work that I thought it was very interesting at the time. And basically what they show is that equatorial waves in our planet, in Earth, have a topological origin. These equatorial waves were known, and they were described and dynamically and physically and so on, but they basically show that it was of topological origin. Okay. So, and this is, probably you know it, very related with the phenomena of El Niño. So El Niño is a current that goes in the equator from west to east, okay? And basically this is, I'm gonna tell you, a topological mode, okay? It gets excited at some time of the year with change in the winds, but this mode is always there, and when it gets excited, it transports heat from one part of the planet to another part of the planet, okay? And basically, the phenomena is exactly the same as you have in a quantum Hall effect. So in a quantum Hall effect, you have a bunch of electrons, a gas of electrons with a magnetic field perpendicular to it, and that traps electrons in trajectories, and because the magnetic field breaks time reversal symmetry, you get this phase with H states that move around the corners. So in the picture of El Niño and coastal waves, what happens is that the rotation of the Earth acts like the magnetic field. It breaks time reversal symmetry in the same way. And all the waves that you have there can move in one direction. And here, these kind of waves are called Kelvin waves. And there are two types. The ones that go along coast. So you have a physical boundary that is solid. So the wave from the sea hits the coast and it moves along the coast, very localized. Or there is another kind, which are the equatorial ones, and they happen in the middle, and this is precisely the Niño. Okay? The other ones, the coastal ones, you can see them in lakes, you can see them in the coast, all over the globe. But the equatorial one, it happens just because the dependence on the latitude of the Coriolis force changes sign in the equator. So this change of sign is like changing the magnetic field from one orientation to the other one. So this creates a physical boundary for the modes, and they localize in the equator. Okay? And that's all you need to have them. So this is just to tell you that at planetary scales, you can have very robust topological modes that affect planetary scale phenomena. Okay? So this is just the math of how this is done. So you can do what is called a shallow water model. It's basically a model that assumes that you have a bunch of water, in this case the ocean, and the length is much larger than the height. So it's a very thin fluid. And when you do the math for this system, you can simplify things and so on. And at the end, you get to a matrix, a 3x3 matrix like this one, that you can diagonalize, and you can calculate the topological invariance in the way I shown before, just finding the genus of the sphere and so on. And you find that there are 3 topological invariants for 3 different bands that you have in the system, and they take values 2, 0, -2. And this is basically telling you that there will be 2 modes in the equator, and these are the modes, are called the Janai wave and the Kelvin wave. And these are localized in the equator, and it's because of this phenomena. Okay? And this has been measured with radar and so on. Okay? So this is what happens in the Earth. But in this paper, in the previous one by Pierre Delplas, what they did was to claim that it could be even more interesting in more exotic places, like in stars, because stars have very different physical mechanisms in action depending on the type of star and so on. I'm not an expert on this at all, so I'm just going to tell you what I learned. And in particular, they talk about LAM waves. LAM waves, you can see them on Earth, because these are the ones that, for example, if you have a volcano explosion, this creates a shock wave, and the shock wave travels between the atmosphere and the crust of the Earth, and is localized and moves very fast. It can go around the Earth many times, and these are shock waves that propagate with a topological origin there. But in stars, they claim that you can have them even without a crust, without a solid mantle, let's say. And it's because in the stars you can have different regions which can be convective, can be radiative, and so on. And as the density and the processes change along the depth of the star, you could have these modes living in between. Okay? So this is the way they think this could be interesting. And well, I think it's very interesting, especially for the people working in astroseismology, which I don't know how much is related with the works that you are doing here, guys. But if you think there could be a connection or something interesting to explore, you can let me know. And I can even be in touch with the authors of these works, and we can try to think about something. Okay, so this was about the topology of stars and planets and so on. So I'm going to move now to quantum mechanics. So basically, in quantum mechanics, topology and geometry arise in the same way. You basically have vector fields with different profiles, and you can have singularities in them. And when you have singularities and you have compact manifolds, like a torus, a sphere, or whatever, you can get topological invariants that are linked to physical properties. Okay? So in quantum mechanics, we basically talk about the Berry phase, which is this one, and it takes the same form. It's just the integral of some curvature along some path, and it's a geometrical result that you cannot remove. It's a phase that you cannot remove with a gauge transformation. And then you have the Berry curvature, which has this form. And then you can calculate from this curvature topological invariants, where the most well-known is the Chern invariant. Okay, it's the one that characterizes the Hall effect physics. So historically, from this, there's been a lot of research on topological systems in quantum mechanics. And there are many invariants that you can calculate for different symmetries and so on. So this is more or less, there was a huge interest in this field when I started my PhD. And when I started basically to connect with my current research, one of the questions we asked was, is this all that is possible in this system when you have a system that has topological properties and so on? And the answer was not, because you can move to non-equilibrium systems, okay? Before, I was talking about planetary waves. This is all non-equilibrium because you have fluids moving and the Earth rotating and so on. But in the previous case, with the quantum Hall effect, it's just a gas, a bidimensional gas with a magnetic field. That's static. But then you can have systems where you also think with the different parameters in a time-dependent way. Okay? So these are called Floquet systems. And basically, the Hamiltonian is periodic in time. The system is not in equilibrium because you are using energy to change the parameters externally. But it has this symmetry, which is a discrete time translation symmetry. So for this, usually, these are interesting because energy is not conserved, but the total phase over a cycle is. So this gives you quantum numbers, and you can use this theory to study the system. And basically what happens is that all the topological arguments that you have in static systems now get enhanced or enriched because these quasi-energies, which are the conserved quantities in time-periodic systems, can also wind. The intuitive way to understand it is when you have a Hamiltonian, usually it's an Hermitian operator. Hermitian operators are basically, if you diagonalize them, it's a bunch of eigenvalues. But phases are defined modulo 2 pi. So it's basically like if you take these energies and you fold them into a cylinder. So now you can have windings where the energies fold around the cylinder, around it. Okay? And this gives you additional topological properties. So this is one of the fields of research where I'm working. And it gives you a lot of new results in topology. So basically, you can get new topological invariants that are not in previous systems. You get new edge modes that are time-dependent, can be propagating and counter-propagating. For example, here there is a picture of a system that could be like a quantum Hall system. And you can have edge states crossing one gap, but also this other gap. And these quasi-energies here are basically winding in the sense that I told you before. And all of this has been tested experimentally with very different experimental implementations in cold atoms, in graphene, in photonic lattice, superconducting circuits, and so on. Okay. So, in particular, I think one of the nicest setups that I know of, it's fiber ring resonators. Okay. And this is basically an optical setup where you have two fibers, which are alpha and beta, and they have a slightly different length. So you send a pulse into one of these fibers, and every time they pass this point. This is a time splitter, a beam splitter. So the pulses separate, and you start making beams with different times of the pulse crossing in the fiber, and then you can recombine them with the original pulse and see basically what is the spectrum. And you can demonstrate that these dynamics of the pulses crossing between the two rings can reproduce the time evolution of tight binding systems or even two-dimensional systems. Okay, so here is, for example, a trajectory. This is for an experiment, and this is the bands measured for a two-dimensional system using this setup. Okay, so one of the interesting things about this setup that we are trying to do now is that you can introduce quasi-periodic driving. So you can modulate this beam splitter in time, and you can do something like Fibonacci sequences and stuff like that, or you can have nonlinear processes because the light, as it travels on these fibers, there can be Kerr processes, so nonlinear effects in the light propagation, that basically give you higher order corrections, and you can reproduce the dynamics, for example, of Bose-Einstein condensate, so the Gross-Pitaevsky equation, and study the dynamics of these type of systems using this experimental setup. Okay. So here is just a bunch of experimental results so that you can see what is the kind of things that you get. So this is real space dynamics. This is the band structures that you measure, and this is a trivial system, and this is a topological one where you have part of the light localized at the edge, and you can see here the edge states crossing between the two bands. So here the bands are identical. The only difference is the presence of edge states because you are in a topological system. And what is even more interesting is that in this kind of setups, because these are quantum walks, the evolution is discrete in time, you can have even more enhanced topological phenomena. Okay? It's what is called string-shift topology. If you are interested in this, I can give you a summary, but it's slightly technical, so I won't go into the details of this. So another topic where I'm working here, and it's basically started with my last postdoc here with Alejandro and with Diego. It's on driven dissipative phases. So it's about the topology of systems that are out of equilibrium, but instead of driven out of equilibrium because of a time dependence, where you change the system in time, it's because you have dissipation. Okay? So when you have dissipation, you can also use this dissipation to improve the system properties or even introduce topological features in the system. Okay, so this we do it with different mathematical techniques. One is called the single value decomposition, and you get funny things, which, for example, what is called the skin effect, which is these edge modes that are localized in the boundaries. Usually in these systems become bunch. So all the modes, instead of just a pair localized, all of the modes in the system tend to localize towards the boundaries, and that allows you to get, for example, amplification of signals in different setups. So this is an interesting field that has very practical applications as well. And finally, to conclude, the other research field where I'm working is basically the natural extension of what I just told you about Floquet physics before. And it's what happens when the fields that you are using to manipulate your system in time, instead of being classical fields, are quantum fields. Okay? So when you assume that, for example, you have a material and you shine light in it, and the light produces the time dependence in the system. To control the system externally, what happens is if this light that you are shining into the system is quantum. So the difference basically is that you get back action between the two systems, and you also get entanglement, because now you are talking about quantum and quantum together, so they can get entangled. So this is a new field that is being intensively studied right now. And from my point of view, it's interesting because it allows you to link, for example, many-body topology. So you can have topological phases that light and matter are entangled, so you get many-body effects in isolated quantum systems. But it also links with non-equilibrium topology in the semi-classical regime, because if you take this light to the semi-classical limit, basically the light is the classical field that you would have in standard Floquet. And in that case, basically, you should recover all the physics of the previous section. So it's a way to study the transition between many-body systems and out-of-equilibrium systems in a very neat way. And in all these systems, it have been found exotic polar returning state, new topological states, and many-body phases that wouldn't be possible without the quantum nature of the light. Okay, and just to mention the last topic where I'm working is with a group in Zaragoza, which is on quantum computation using molecular spins. This is related with this because basically molecular spins are big spins, quantum spins, and they are trying to use them to make computations by coupling them with resonators. So the resonators are exactly the cavities that we would use in these materials, and the materials would be the molecules. So you can use the cavities to manipulate and operate quantum operations in these computers. So this is the last topic what I'm working on, and this is the summary. So if you think that any of the topics that I talked about could be interesting for your research, you want to know a bit more about it, and you just think that any of these can be useful or interesting for you in any way, just let me know. We can look at it. And And yeah, thank you very much for your attention, and I'm around if you need me.
Well, thank you very much for this very nice talk. There are questions? Oh, a lot. Yeah, so, Álvaro.
Look, it was a real challenge what you tried to do.
Yeah, I know, it took me some time to...
A real